Here we go, everyone. This is the final video in chapter 14 and the final video of the overall DB2 course. We will use that video to discuss the cost formula for the index scan. Okay, so this video will address index scan just like the previous video addressed sequential scan. Let's invest some thought in the development of cost formula for index scan, which of course is a somewhat more intricate undertaking than for sequential scan because there are two data structures involved that the system will process: the heap file as well as the B+ tree that supports the index condition. So if you have a look at a typical query plan snippet that contains an index scan, you will see mentioned the particular index. All right, so we will probably need the metadata about this index. Well, the height of the index, the size of the index in terms of pages and leaf level entries and so on. And of course, we would need information about the base table that is being processed. There would be output expression involved in the setup of this index scan, and there would of course be an index condition that would be evaluated for all the entries that we scan in the index leaf level. And of course we would use this particular literal here to guide our search during the B+ tree descent. All right. Well, all of this has to be incorporated in the cost formula for index scan, and the upcoming minutes will show you how this is being done in PostgreSQL. Well, you will see that the index scan cost model is indeed a three-part cost model that separately accounts for the B+ tree descent. We first need to descend inside the B+ tree from the index root node to the leaf level before we can start scanning the leaf level and indeed produce rows during that index scan. So that B+ tree descent will add to the startup cost of the index scan. All of this has to be done before the first row can be produced. Then there will be, of course, the index leaf level scan. We will traverse the sequence set of the B+ tree index in the desired range, okay, because we are evaluating a range query like this one here. And of course, there will be the third component, the heap file access. If we are processing an index-only scan, well, there would be no heap file access, and we expect reduced costs, and we will see that in the playground experiment that we will perform in a few minutes. But in general, there will be heap file accesses. The RIDs in the index leaf levels will point us into the pages of the heap file that contain the wanted records. And well, we have to perform I/O to reach that heap file. And we will see that there will be a difference whether that is a clustered or a non-clustered index. We, of course, would expect clustered indices to lead to sequential I/O, while non-clustered indices lead to random I/O. And well, of course, this would be reflected in the space dollar cost that is being assigned to the index scan. All right, let's dive in. We would, of course, need meta information next to the default cost model parameters that are defined in the config file of PostgreSQL. We would need information from the database meta level. We have seen these three guys already when we were talking about the sequential scan: the number of rows and pages in the input file and the selectivity of the predicate that we are assessing. And well, of course, we would need information about the index that is involved, the height of the index, so the number of inner node references that we have to follow inside the B+ tree to reach the leaf level. There would be the number of rows held in the leaf level of that index and the number of pages that make up the leaf level of the B+ tree index. All right, all of this should be expected. And then there is also correlation. A correlation would be a parameter of the index that measures the physical ordering of the index leaves in comparison to the ordering of records inside the heap file. Okay, so this is all about clustering. In a perfect world where the order in the the order of records in the index leaf level coincides perfectly with the order of records inside the heap file, we would have a correlation factor of 1.0. If that ordering is actually inverse, then we would have a correlation index of -1. So after clustering, we would expect a correlation of 1, and we will play with such an experiment when we switch over to the terminal. And well, we will also see the unclustered case, and we'll see that we will suffer from higher estimated and also higher real cost. Okay, all of these can be queried using the metadata tables of PostgreSQL, and we will have a closer look at that when we switch over to the terminal. All right, so first phase, the B+tree descent, which actually defines the startup cost of index scan. All right, well, the descent through the B+tree, of course, will be influenced by the height of the B+tree, and the height of the B+tree is actually, of course, correlated with the number of rows that are stored inside the B+tree, the number of index entries that we want to store there. We would try to operate over B+trees that have the maximum fan out, which would be 2 times the order of the B+tree. That would be the maximal fan out, and well, that would be the base of the logarithm that we would have to apply to the number of index entries to arrive at the height of the B+tree. All right. While we descend through the B+tree, while we follow this particular path from the index root to the leaf level, we would have to perform binary searches in each of the inner nodes. Binary searches that would identify the pointer to the next inner node that we have to follow to actually establish this path through the search tree. Okay, so the number of these binary search comparisons would be the following. Of course, we would inside each inner node, and we assume that all of these inner nodes are perfectly filled, so there is no space wasted on our inner nodes. All of them carry the maximum number of index entries, so that would be 2 times O index entries. Performing a binary search over these would involve log to the base 2 times O comparisons. This would happen on each of the levels of the B+tree. That's why we multiply with H here. Okay, so if you multiply that, then you will arrive at the log base 2 of the number of index entries that you will find in the B+tree. Okay, so that would be the number of key comparisons that we have to perform during the descent. Well, all of this adds up to the startup cost that we will see for our B+tree descent. There would be startup costs for the index scan that are attributed to the startup of the predicate and the expression associated with the index scan. And we have seen that before. This is no different to the sequential scan case. Probably these will be zeros unless there are subqueries that have to be evaluated, and that would then add to the startup cost of predicate or expression. All right. To that, we have to add the cost for the B+tree descent. So that would be the number of key comparisons to be performed during the descent. And these would be multiplied with the CPU operator cost, which makes sense. These are comparisons that we would have to perform. And there's, of course, further processing that has to be done. We have to process the index node themselves. We will, during the descent, we will find H of these. Then we will also access a page on the leaf level. So that makes H plus 1 nodes of the B+tree that we would have to process, and that would be some fudge factor here that accounts for all the effort that we have to invest to process such an index node. Right, so that would be an additional factor that is applied to the CPU operator cost, and we would add all of this to account for the CPU cost that is involved in performing the B+tree descent. All right, so that would be the first cost component. The second component would be the leaf level scan. Okay, so once we've reached the leaf level, we would scan along the sequence set of our B plus tree to find all the index entries that are in the search range between some lower value and some upper value high here. You know the drill. We have talked about sequential scans in the index leaf level of a B plus tree many times already. All right, so such an scan of the leaf level would of course incur index CPU cost and index IO cost, as they are termed here. So CPU and IO would contribute to the overall cost. So let's talk about the CPU cost first. Well, this would be the number. This would be the number of rows that we have to process while we scan the index leaf level. That would be the number of overall index entries multiplied by the selectivity of the predicate. The more selective the predicate, the tinier the selectivity value, the tinier would be the range, the number of rows that we have to process. Okay, so this is the fraction, the part of the sequence set of the B plus tree that we have to process indeed. For each of these rows inside the scan range, we would have to decode that particular index leaf entry, we would have to separate the key value and the row ID and so on, and just perform some CPU work there. And this is accounted for by the CPU index tuple cost. To that, we would have to add the run cost for the predicate. For the predicate that, for example, evaluates the comparison with the upper range high here, so that we don't exceed the rightmost range of our range scan. Every row would have to be checked against this upper high limit to make sure that we do not pass the range's upper end. Okay, so all of this would add up to the index CPU cost. The index IO cost would of course also involve the IO access to all the pages that are stored inside the index leaf level here. We won't have to scan the entire index leaf level. We will only scan this particular fraction of the leaf level inside the index. This is of course already also determined by the selectivity of the predicate. The more picky the predicate, the less pages we would have to access. Here we rather pessimistically assume that the pages that make up the B plus tree leaf level, that they are not clustered, right? So this is not about the clustering of the heap file. This is about the clustering or the access of the pages that hold the B plus tree index leaf level. We pessimistically assume that these are not sequentially allocated on the secondary memory device, and thus account with random page cost here. All right, so that would be the leaf level scan. And then, of course, there's the component of performing heap file access. Right, so once we have scanned the index leaf level, or while we scan the index leaf level, we also have to peek into the heap file to grab the wanted records from there. And well, the heap file access part of the cost formula, the heap CPU cost and the heap IO cost, they account for these accesses into the heap file. All right, so let's see. What about the heap CPU cost? So the number of references that we will have to follow inside into the heap file is just this: is the number of row index entries multiplied by the selectivity. These are the number of rows inside the index scan range. We have seen that before. For all of these rows, we would once we have accessed the correct heap file page, we would have to access this particular record or row on the heap file page. We would have to decode that particular row, just like we have to decode a row during a heap file scan, and that would incur CPU tuple cost. For all of these fetched rows, we would then have to evaluate the output expression. Right, because this defines the output of our index scan. So, well, all of these rows would also incur the run cost of the output expression. Okay, so much for the heap CPU cost. Right, and now to the IO cost, which of course would be influenced by the fact whether the index is clustered or non-clustered. The more clustered the index is, the cheaper will be the heap I/O. All right. So what we will do here is to linearly interpolate between the two extremes, that there is a completely unclustered scenario and a completely clustered scenario. And we will use the correlation, that metadata parameter that we have read and extracted from the PG catalog tables for our particular index. We will use the correlation and square it to derive at the clustering factor for this particular index. The correlation is a value between -1 and 1, so the square will be a clustering factor between 0 and 1. This will be a measure of how clustered the records are, a measure of how well the ordering of the rows in the index leaf level and the ordering inside the heap file coincide. Well, if this particular value is 0, all right, if this particular value is 0, well, then we would incur the unclustered I/O cost case. All right, so the heap I/O cost would be determined by the completely unclustered case. And the next slide, slide 28, will show you one particular formula, cost formula for the unclustered I/O cost. If this value is 1, which would be the other extreme, the perfectly clustered case, then you will see that this addition here leads to unclustered I/O cost minus unclustered I/O cost plus clustered I/O cost. Okay, so indeed, then the clustered I/O cost would completely determine the cost, the heap I/O cost of our index scan. Normally, that would be an interpolated value, linearly interpolated value between the unclustered I/O and the clustered I/O cost. This is how PostgreSQL incorporates the correlation factor or of the index into the estimated I/O cost during the heap file access. So let's briefly look at how we could assess for unclustered I/O cost and clustered I/O cost. All right. This left-hand side of the figure here, well, you can see that because all of these page pointers are so neatly ordered. This obviously is the clustered I/O cost case. All right, so following the page pointers, the RIDs from the index leaf level into the heap file, on the very first access, this very first access here on the left-hand side, this one, well, this will hit a page that will probably not be in the database buffer. We will probably have to seek on the disk to access this particular leftmost page in our heap file scan here. So that would incur one-time random page cost. From then on, we would of course follow further references during our index leaf level scan here, but they will hit sequential pages inside our heap file. If we are lucky, then multiple such references will lead to the same heap file page even. All right. So what we will find is that well, this would be the number. This would be the number of overall pages in our index file. Well, this is the fraction of the file that we will probably have to read. The selectivity of the predicate defines the portion, the size of the portion of the underlying index file, input file, the underlying heap input file that we would have to scan. Of course, one page has already been accounted for, the very first page of this index scan, so we would subtract that here. But all of these IOs would be sequential IOs because we simply scan the file in the requested range here from left to right in sequential fashion. All right, so that would be the clustered IO cost. In the unclustered case, well, everything is a jumbled mess. Everything is chaotic. There is no sequential page cost to take into account here. It will be random IOs. It will be random page IOs that will lead us here and there and maybe here back again. There will probably be no caching effects whatsoever. We will have lots of disk seeks. So that would be unclustered IO cost. And well, how many pages would we access? Well, probably all of the pages, or in a pessimistic case, all of the pages of our heap file will carry some wanted record that we would have to access. And so, well, the entire pages, the entire number of pages of the underlying heap file goes into the equation here. And well, all of these pages will be accessed in a random fashion. All right, which is of course the worst case that can happen to us. Whew. So that would make up all the parameters that we need to assess the overall cost of an index scan. We would have the startup cost, which if you recall also accounts for the B+3 descent. We would have the index scan cost, index leaf level scan costs with their CPU and IO components. And then we would have the accesses into the heap file, where this component accounts for the clustered and non-clustered case. All right, so that completes the cost formula for our index scan. What you will find here on slide 29 is only an additional comment on the correlation factor and how that's being computed inside PostgreSQL. So let's not look too closely at that. But well, it's a typical correlation in that also builds on this array of pos values, which is represents the position of one particular row inside the heap file. Well, if that heap file would be perfectly ordered according to the A column that we are looking here, right? Well, then the positions in which we find the files, if we find the records inside that file in sorted order, they would be just found at position 1, position 2, position 3, up to position n here. All right, so if the AI are ordered, then their positions will be ordered in a perfectly clustered file. And if you look at that, well, if you look at this fraction here that defines a correlation index, in a perfectly clustered file, the positions here, they coincide, the position of value AI coincides with I. So what you see above and below here is just the same values. So the correlation would be 1 in this particular case. Okay, we will also see that if we switch over to the terminal and see all of this in practice. Let's do that. Okay, one last switch over to the PostgreSQL terminal. All right, what we see here is indeed our Scratch database again, and we are looking at the index table again. Okay, well, let me show you the index table here, the definition of the index table. We have seen that before, but I would like to point out that there are now 2 indices defined. The index on the A column, and this will be the index that we are going to use in our playground experiment. And then there is an additional index on the C column. And you can see currently the files, the rows inside the heap file for our index table are clustered according to the C index. That makes, of course, the indexed A here an unclustered index. Okay, so well, clustering by index C was simply done to ensure that, well, this indexed A is indeed an unclustered index. Later on, we will cluster the heap file according to the A index and then can access the clustered case. All right. So before we can start, we need some metadata from the catalog tables of PostgreSQL. For example, the number of rows and the number of pages in the heap file itself and in the 2 participating indices. Let's have a look at that. All right. Okay. So, well, there's 1 million rows in the underlying tables because we are talking about dense indices here, in which each row of the underlying table is reflected in the indexes. Of course, they will also have 1 million rows in their index leaf level. Okay. Well, the number of pages in the index file itself is 9,343. Okay. Well, the indices are, and we would hope so, are a bit smaller, like, well, be 1/3 of the size, maybe 1/4 of the size here. Okay. because we will be talking about index A in particular, we will have to take into account this size of the number of pages in the A index, which is 2745. Okay, that would be the first bit of metadata. Then we would access the correlation factor for the A index, and we don't expect 1 here. We expect well, a significantly lower value. The order of records inside the heap file is according to their C values, which does not coincide at all with the order of the A values. So let's see what we find here. Oh yeah, indeed. So that's a value that is close to 0, which means completely random order. All right, so this is indeed the unclustered case for index A. And then, because we will talk about the index A in the upcoming queries, let's also check the height h of this particular index. We have seen that typically height, index heights are between 1 and 3, and indeed this index has a height of 2. So I think this is all the parameters that we know, that we need to know to perform our cost formula computations here. Okay. This will be the query that we are going to access. All right. This is indeed a predicate that should be very well supported by a B+tree index. And to make sure that indeed that particular B+tree is actually being used, we will disable sequential scan for now. So this enforces index scan over an unclustered index. We will switch off bitmap scan, which you know would be the preferred method by the system if the index is unclustered. All of this will be switched off just to make sure that we are talking about the plain index scan here. So switch off, which is of course very unwise to do. We will use an index scan, although it will probably be rather costly. All right, and then let's assess the cost of this sample query here. Okay, indeed an index scan has been planned. All right, the index condition, yeah, okay, so the B+tree, although it's unclustered, it can support this particular index condition. That's a range condition that is very well supported by a B+tree on the A column. And this is the output expression, very simple arithmetic expression that we've seen before. Right, well, this is the estimate of the number of rows that can qualify. It's about 10% again, and yeah, this is the overall total cost. It's 40,000, which is way higher than the 23,000 that we've seen in the sequential scan case. So it really is a sign. The system is convinced that index scan is really not a good idea here. Sequential scan would fare much better, but, well, unfortunately, we have switched sequential scan off. All right, to follow the instantiation of the cost formula, I've again instantiated a file in my interactive calculator here. All right, these are the default cost model parameters. We have seen these before. We now need a bit more of data from the metadata level of PostgreSQL. We need, of course, the number of rows in the input file and the number of pages in the input file. We have seen these. We have just queried these as 9,343. The number of rows inside the leaf level of our index will, of course, be 1 million because we are talking about a dense index here. The number of pages in the A index is 2,745. The meta level has just told us so. And the index height is 2. You see that we are very well prepared here. But the correlation factor, it appears that I have made some experiments with a completely clustered index here, where the correlation factor for the index has been different. Let me check again here. And then enter the correct correlation factor. All right. So I've just checked the file, and the correlation factor should indeed be 0. Okay. All right. So that would be, well, let's not be. Hey, let's be distracted by this by this output here on the right hand side. Now this is the correct correlation factor. Okay, perfect. Okay, so it's now time to perform the cost formula computation for this particular query. I've reproduced the query here. The number of rows that were estimated by the system to be produced by this query is, let me check again. Okay, 102,362. Is this right? Yes, I think that's right. Okay, everything else follows from our discussion on the slides. The cost formula on the slides, I've just transformed it into this interactive calculator format here. We can assess the selectivity of the predicate, which would be again about 10% here. There would be the startup cost of the predicate and the expression, and they would be both 0 because there is no subquery involved, nothing like that. Okay, the startup cost of our index scan overall would of course account for the B+ tree descent. So we have seen that this of course depends on the number of comparisons that have to be performed during the B+ tree descent, and that's this term here. All right, and then there's of course effort involved because we have to process all the pages that we encounter during this descent during inside the B+ tree. And this is a measure of the effort that we have to involve in processing one such indexing node there. Okay, and well, this is the CPU operator cost that we multiply. So this is the CPU effort involved during the +3 descent. Okay, and that would define the overall startup cost of the overall endeavor. It's 0.42. If I switch back to the terminal again here, 0.42 is indeed the startup cost that PostgreSQL also assigned. Now for the other two components, the leaf level scan and the heap file access. All right. So during the leaf level scan, we will of course have to evaluate the predicate. The run cost of the predicate is essential now that we have to evaluate for all of the rows inside our index leaf level scan, so that we don't exceed the upper limit of our range scan. And well, you can see that this is just 1 times the CPU operator cost because we are facing this simple comparison, less than or equals comparison here. Okay, so that would be the run cost of a single invocation of a predicate, but the overall CPU cost during the index leaf level scan would of course be the number of rows that we have to scan. This of course is defined by the selectivity of the predicate. For each of the scanned rows, we would have CPU index tuple cost, extract that particular index entry from the leaf level page, and then evaluate the predicate, which is the run cost of the predicate here. And this amounts to the index CPU cost on the right hand side. And then there's of course also the index IO cost. We have to fetch the pages that host the index entry themselves, the pages that make up the sequence set of the B+ tree index. And that also would be a fraction of the number of pages in the leaf level of the index. The fraction is of course defined by the selectivity, and we pessimistically assume that we have to perform random page cost as discussed on the slide again. Last component, heap file access. For each row that could qualify and that would be accessed during the heap file access, we will have to evaluate the output expression. And the output expression involved a multiplication and an addition that makes 2 times the operator cost, and this is accounted for here. The heap CPU cost, of course, this would be the number of rows that we would have to fetch from the heap file. Each of these rows would have to be decoded. For each of these rows, we would have to evaluate the expression, and that makes up for this particular cost contribution here. And then there is our preparations for the evaluation of the heap IO cost. That would be a linear interpolation between the clustered and the unclustered IO cost, if you recall. Okay. So the clustered IO cost would incur 1 random page IO, the leftmost page inside our heap file scan. And then there would be a fraction of the input file that we would have to scan. The fraction is of course again defined by the selectivity. And but all of these page accesses would be sequential, just as clustered IO can give us. Perfect. In unclustered IO case, we would probably have to touch all of the pages of the input file in random fashion. And that would be this super large contribution of cost here on the right hand side. Of course, we would use these two extremes of cost that could hit us in this linear interpolation of the heap IO cost. All right, and in that interpolation, you will see that the clustering factor, the square of the correlation here, makes an appearance, and for exactly the reason that we have discussed on the slides. All right, now all the components are there. All the components are there. We can add them up to the total cost, the startup cost, and the run cost for the index scan, if you will. And that leads us to 40,798 space dollar. And this is what Postgres reports as the estimated cost value here. All right, so it really appears that our modeling of PostgreSQL internals match what we've seen on the slides here. All right, perfect. So now let's switch to the clustered case, and we would of course hope that the heap IO cost really drops. Okay, so let's see whether we can indeed see that. So we will now recluster the index table according to the A column, or to the B plus tree index over the A column. And then assess all of the new file that will be written during the clustering in this analyze here. All right, so let's do that. All right, that would take some time, but it's time well invested. We will benefit later on when we evaluate queries over the table. All right, done that. Okay, so what we now expect, if we assess the correlation again, the correlation for our index over the A column, then we expect the value of 1 here now. The clustering led to a perfect correlation of orderings in row orderings in the heap file and in the index leaf level. And indeed, there is the 1. All right, perfect clustering currently. All right. So then it's time to reevaluate this particular query again. The same query, nothing has changed, just the index has been reclustered. All right. Oh, this looks way cheaper. We were talking about cost of more than 40,000 space dollars now. Now we are in a tenth of the cost range here. Okay, so it's about 4,000 space dollar that we have to invest. Let's see whether our cost model can correctly reflect that. Here we are again. So let's adapt all of these parameters. So nothing here has changed. Of course, the correlation of the index has been changed. It's 1.0 now, the perfect case. Okay, well, the selectivity of the predicate has been reassessed by the system because we have run an analyze that led to a different sample of rows. So that sample, the system said that 99568 that is the expected size of the output, which is of course derived from the known number of rows that go in and the estimated selectivity. Right, so the estimated selectivity by the system has been 0.09557. All right, I think this is all we need to change here, right? If I'm not mistaken, that should now perfectly model the behavior of a clustered index scan. Nothing has changed here. Nothing has changed. Of course, now in this linear interpolation, we are much closer to the clustered IO case. Well, we are at the clustered IO case in this particular case. And well, we are rewarded with that. It's just 4,098 here of the cost that we see, and that is really close to what PostgreSQL has outputted here. So there's some deviation here of about 1 space dollar, but well, there is probably some rounding going on here, so that's good enough for us in this particular case. Okay, so unclustered case and clustered case could be assessed perfectly well. As the final bit, let's look at the very interesting case of an index-only scan. So in this case, the heap I/O cost during our third phase, the heap file scan, should indeed be 0. A true index-only scan will never touch the heap file, and we will make sure that this is indeed so by running a vacuum first here. As you could know that, or recall, I hope so, that will perform a visibility map update. Well, the visibility map will indicate that there are no dead rows actually on the heap file pages. There are all entries in the index leaf level that we will find will correspond to indeed live rows inside the heap file. So there is no need to go and check the heap file indeed. Let's try and run vacuum here to construct this perfect situation for the system. Perfect. So now this is the query again, but please note that in this output expression, I'm now accessing the A column. The A column over with the A index obviously has been built. The A values are present in the leaf level of the B+tree index. There is just no need to access the heap file. This should really lead to a perfect index-only scan, and that should be even cheaper than the 4,000 space dollars that we have just seen. All right, yeah, index-only scan has been planned. Perfect. Everything is as expected, and well, indeed, the space dollar assignment of course is indeed even less. 3,200 space dollars here. That would be the best case, right? And well, this is also perfectly well modeled by our cost model over in the interactive calculator. I brought that case with me as well. So this is the query that we are looking at now. As you can see, this is over the output expression that is referring to the indexed column. So index only scan is indeed an option here. Let me adapt the number of rows or the selectivity estimate that this system has found, 95568 in this particular case. This has been updated. Yeah, okay. So the selectivity has been updated. Everything else remains the same. Everything else remains the same. Nothing has changed here. Well, in the section on the heap file access, this third component of our index scan cost, well, in this case, there won't be any heap file to process. We are in the perfect case where the visibility map tells us that an access to the heap file is just not needed. There will be heap I/O costs of 0. Okay. Well, still, we would need to process the rows that we found during this index leaf level scan. We find these A values in the index leaf level scan. We find that many of these, for example, and we have to process these values and we have to stick them into the output expression. Nobody saves us from computing the output expression, so these costs will still hit us. But the major cost factor of heap I/O cost, they will be 0. Okay, and that leads to an overall cost for an index only scan of 3,202 space dollars. This is indeed what we've seen here over on the PostgreSQL side of things. All right, so this is a glimpse of the PostgreSQL abstract space dollar cost model, the information that the system needs to guide its search in the vast search space of equivalent plans that we can consider for the evaluation of a given SQL query. This abstract space dollar cost model value defines what is the better plan of two given plans. All right, back in the X-Wing repair shop. This is indeed the end of this particular video. It's the end of chapter 14 on query optimization, although there would be so much more cool stuff to cover, but not in this particular semester. It's also the end of the DB2 course. And I would like to sincerely thank you for your interest, that you stuck with me for all of these, I think 83 videos. This is a major effort on your side. It's also a major effort on the side of my my assistants and myself. I thank you for your interest. I think we have done really well during this pandemic semester. Let's hope that things clear up and look brighter in the future. I'm looking forward to meet you in person again, face to face, and talk about all cool kinds of database technology in the upcoming month, semesters, or years. Hope to see you around. Take care, folks, and thanks for your interest. Bye-bye.